Conservation of mechanical energy. The mechanical energy, E mechanic of a system, is the sum of its potential energy U and the kinetic energy K of the object within it. So E mechanic equal to kinetic energy plus potential energy U. In an isolated system, where only conservative forces causes energy changes, the kinetic energy and the potential energy can change, but their sum, the mechanical energy, E mechanical of the system, cannot change. So delta U, by definition, equal to minus W. This is the work done by the conservative force. This is the potential difference of this conservative force. And also, we know the work kinetic energy law, delta K equal to W. And we put this together, we found W minus W cancel out. We get the change of mechanic energy, delta E, equal to delta K by delta U equal to 0. And delta K is K2 minus K1. Delta U is U2 minus U1. This is equal to 0. Okay? So we get another form from here is K2 plus U2 equal to K1 plus U1. Principle of conservation of mechanic energy. Delta E mechanic equals delta K plus delta U equal to 0 for an isolated system. We write delta K, K2 minus K1. Delta U, U2 minus U1. We rewrite this formula. We get K2 plus K, U2 equals K1 plus U2. What is this? This is the mechanic energy at point 2. This is mechanic energy at point 1. When the mechanical energy of a system is conserved, we can relate it the total of kinetic energy and the potential energy at one instant to that at another instant without considering the intermediate motion and without finding the work done by the forces involved. The principle of conservation of mechanical energy allows us to solve problems that would be quite difficult to solve using only Newton's law. This very powerful formula. Look, this is a swing. At the central point, we know the speed is largest, and look, potential energy is the lowest. So this is kinetic energy is the largest, potential energy 0. And it goes down, the gravitational potential increase, and the speed goes down. So the kinetic energy reduce, potential energy increase. And when it goes to the top, it stops there. The potential energy it get maximum, the highest, and the kinetic it gets 0. And need to return back. You get the speed up, so kinetic goes up, and the lower, so potential is the lower. Finally, at this local point, you get velocity get maximum, kinetic energy maximum, and the potential energy lowest. And you return this one.
This pendulum ball will be released from the height marked on the screen. When it reaches the bottom of its swing, a post will stop the top part of the string, but the ball will continue moving. How high will the ball rise on the other side of the swing? Lower, higher, or the same as the release height? The ball rises to the same height because the energy is conserved. Here's the demonstration repeated with a different initial height.
This person will put his face on the line to demonstrate faith in the principle of energy conservation. A bowling ball pendulum is released from rest directly in front of the person's face. If energy is conserved, the ball cannot rise higher than its release point, and his face is safe. Should he be willing to bet on that? Let's find out. The ball is released and misses by a nose.
Raising a mass increases its gravitational potential energy. We'll use this triple track to show that this energy is conserved as it changes from one form to another. We'll release a rubber ball down each of these 3 tracks. Each track has a similar downhill section, but the uphill sides have different slopes. If a ball is released from the top of each track, how high will it rise on the other side in each case? Here's the ball rolling down the first track. The second track. The third track. The ball rises to the same height from which it was released in each case.
Sample. In the figure, a child of mass m is released from rest at the top of the water slide at height h 8.5 meter above the bottom of the slide. Assume that the slide is frictionless because of the water on it. Find the children's speed at the bottom of the slide. In this case, if you calculate the work done, it's very complicated. So instead, we use the concept of potential energy. Because the kinetic energy, mechanical energy conserve. So we see the mechanical energy at the top equal to the mechanic at the bottom, including 2 parts. Kinetic energy at top plus potential energy at top. This is kinetic energy at the bottom plus kinetic at the bottom. This one is half mvi squared. This is mgy top. This is half vb squared. Vb, what we want to find. And this is the bottom is mgy. From this equation, we find VB squared equal to the T squared, M cancel out, 2G Y top minus Y bottom from this equation. And as you see this one, we know this for everything. This is the 0, and YB is 0. So YTYB is H. This is a 0, so YB squared equal to 2YH square root. Get it? Much easier to do it. Sample. A 61.0 kilogram bungee cord jumper is on a bridge 45.0 meter above a river. This is 45. The elastic bungee cord has a relaxed length L, 25.0 meter. Assuming the cord obeys Hooke's law with a spring constant 160 Newton per meter. If the jumper stopped before reaching the water, what is the height h of her feet above the water at her lowest point? Now, when you jump off, the cord, spring cord, extend D, okay? That's maximum. When it's at rest, okay, and we will see what is the h. According to the conservation of mechanical energy, so delta K plus delta U equal to 0. Delta U including 2 parts. One is that the cord, spring cord, one is gravitational force. We put number inside. Delta K is 0, from 0 to 0. So delta K is 0. Delta UL, it originally is at relaxed state, and you extend D. So it has potential energy half kT squared. Originally it doesn't have, so delta U1 is this one. And delta G, delta UG is mg delta 1, Y is minus L plus D. We put this one inside, and we get here, okay, delta X equal to 0. Move this one, have MD, minus this one equal to 0, okay? So, from this one, we can find the D. We get a D equals 17.9 meter. Now, D is 17.9, this is 25. Altogether, here is 45, so we can find H. H equal to 45 minus the length minus the D. So 3.1 meter, pretty. Now, if she is 1.7 meter high, then it's only 0.4 meters. This one, very scary. Reading a potential energy curve. Once again, consider a particle that is part of a system in which a conservative force acts. This time, suppose that the particle is constrained to move along an x-axis while the conservative forces does work on it. We can learn a lot about the motion of the particle from the plot of the system's potential energy Ux. Finding the force analytically, we know that if we define delta U equal to minus W, and W equal to F dx, very small amount. Okay? So from here we get Fx equal to minus du dx. Get this one, okay? So once we know the potential energy, we can find the F at some point, right? We can check this result by putting Ux half kx squared, which is the elastic potential energy function for a spring force. The equation then you do the derivative with respect to x, and you get kx and minus, you put the minus here, minus. What is this? Which is the Hooke's law. Okay, it's a Hooke's law, right? Similarly, we can substitute Ux mgx, which is the gravitational potential energy function for a particle of mass m at height x above the Earth's surface. This equation, we do this one, mg minus, okay, it's minus. So we get F equal to minus mg, which is the gravitational force that acts on the particle. So we prove this one is right. The potential energy curve. Now, this red line is a potential energy curve at some point particle. This is potential energy. This is the location x. Okay. We know the mechanical energy conserved, so potential energy plus kinetic energy equals mechanical energy. In this case, 5.0z is the mechanical energy for this special case, okay? The case. And we have the turning point. This point is called a turning point. Why? Because the potential equal to the mechanical energy totally. So this case, at this point, kinetic energy is 0, velocity is 0. So it goes from here to here, it comes back. At this point, the velocity is 0. We call it turning point. Okay. The particle changes direction. That's this one, we call it x1. Equilibrium points. Now, this one, this one, this one, this one. These three are equilibrium points. At any point to the right of x5, the potential is the same. Okay? That's equal to the same. So there's no force on it. So it must be stationary. A particle at such a position is said to be in neutral equilibrium. And we know this one. U is the same. So du dx equals 0, F equals 0. It does not have any force acting on it. Now, let's do another curve. This is a minus du dx. So this is the one. This is a minus du. This is a force. Okay? The particle remains stationary at the unstable equilibrium point, like this point. We call it unstable. Why? If it is displaced even slightly in either direction, a non-zero force pushes it further in the same direction, and the particle continues to move, such as x3. We look up at this point. We call it unstable equilibrium point. If we move to right, look at this one, and then we have a force positive, push it further right. If we move to left, and you have a negative force, move it further left. So it's unstable. It will not come back to the original point. The particle is stuck at the stable equilibrium point. Now, this x2 and x4. It cannot move left or right on its own, because if we want to do so, we need to require a negative kinetic energy. Also look at this x2. If we move to right, positive direction, and it will exert a negative force to the left. So it will come back to the original point. If he move to left, and you have a positive force acting on it, move it toward, make it come back to the original one. So this is called stable equilibrium point. Okay.
Here is an arrangement called an energy well. The V-shaped bottom of this track is a potential well in which a ball can roll back and forth. If the ball has insufficient energy to escape over the top, it is trapped in the well and can only oscillate back and forth. How much higher than the low side would it have to be released from in order to escape? A release point only slightly higher than the low side is sufficient for the ball to escape.
Sample. A 2.0 kilogram particle moves along an x-axis in one-dimensional motion, while a conservative force along that axis acts on it. The potential energy Ux associated with the force is plotted in the figure. This is a red line. Okay. If the particle is placed in any position between x equals 0 and x equals 7.0, it would have the plotted value of u. This is a u. Okay. At x 6.5 meter here, it would have the plotted value v u at, okay. Sample. A 2.0 kilograms particle moves along an x-axis in one-dimensional motion, while a conservative force along that axis acts on it. The potential energy Ux associated with the force is plotted in the figure, the red line. If the particle is placed in any position between x0 and x 7.00 meter, it would have the plotted value u. At x equals 6.5 meter, the particle has velocity v0 minus 4.00 meter per second I. That means negative direction of x. Okay. Question A. From the figure, determine the particle speed at x equal to 4.5 meter at this point. Okay. We see that at x point signal is given. This is a u equal to 0. And the v equal to half mv0 squared. We can find it out. Okay? Because give you everything. And U plus K is the total energy, the mechanical energy. Right? Yeah. So it's 16 joule. Now, because mechanical energy conserved, when it was 4.5, the mechanical energy equal to 16.0 either, right? And we know the potential energy is 7. So we know K1, okay? So kinetic energy, K1, you get total mechanical energy minus potential energy, 16.0 minus 9.0. And this one equal to half mv squared. We have V, we got a V1, okay? 3.0 meter per second per second. Question B. Where is the particle's turning point located? We know the mechanical energy total is 16 joule. Okay, so it should be here. When the potential energy is 16 point, the kinetic energy is 0 is the turning point. Okay, where's the turning point? Now we look at it. Now, 1 to 4, this is a straight line. At 1, this is a 20. At the 4, this is 7. I want to find where is the 16. This is a very easy question for you, okay? I'm not going to do it, okay? We can tell you the x is 1.9 meter, okay? 0.19 meter.